Welcome back to BAS 120. We're going to go through Chapter 4 on descriptive statistical measures. So what we're trying to do here is describe the data. So some of the topics is we'll talk about the difference between a population and a sample. Then we'll talk about how we can describe data via measures of location. Where is the center of our data? Might be an example. Then we'll talk about measures of dispersion. What's the range? How wide is our data? Then we'll talk about some measures of shape. Is it skewed in one direction or another? Or is it very thin and tall or very wide and flat? Then we'll talk about a little bit how we find the mean of grouped data. Then we'll talk about measures of association. How can we look at if there's any correlation between one set of data or one variable and another variable? Then we're going to spend a little time talking about what if we have what's called an outliner, a number that's very much different from the rest of the data. Is it an error or do we include it? What do we do? And then we're going to wrap it all up by talking about how do we statistically think about this descriptive stuff so that we can use it in our day-to-day lives, and we'll give you a few examples. So the first topic, which I think most of us will probably intuitively have some thoughts on, is there's two different types. There's what's called the population, which includes all the data, all the items in the data. Now, rarely do we have all of the population, but if we do, those are called parameters. The population is called parameters, and when we get into notation, you'll see why that's a little bit important. We'll get to that on the next chart. A sample is a subset of the population, and these are called statistics. So oftentimes what we do is we gather numbers from a sample so that we can predict or project the population, or another way of saying it is we use statistics to project or estimate what the parameters of the population are. So what do we mean by those parameters and statistics? So one might be the mean or the average, commonly a measure of location. Mu would be the parameter or the population mean, and X bar would be the statistics or the sample mean. Standard deviation, which is a measure of dispersion. Sigma would be the parameter, the population standard deviation, and a small s represents the standard deviation of our sample. The size of the population or sample, capital N is for the population, small n is for sample. And for proportions, this is where we have oftentimes with categorical data, we have yes, no, pass, fail. Those are proportions. We have pi for the population proportion and p for the sample proportion. And another handy one is summation is represented by this. So you may want to keep these handy so that as you read through all the statistics, you can understand the language or the notation. So that's some background on population and sample. Let's talk about measures of locations. Okay, so what we're interested here is where's the center? Where is most of our data? If you think about taking a test score, oftentimes the instructor says the class average was this, the median was this, the middle score was this. So if you're familiar with those, you're familiar with this. The three most common measures of location are the mean, which is the average. And what this chart does is it tells you what these are. It describes it a little bit. And then we'll talk about how to do it in Excel. So in most statistical software packages will have a way for these to be calculated. So the mean is what most of us call the average. You add up all the scores and divide by the number of scores. And you can do that in Excel. You just say average and you highlight the range and it'll calculate it for you. And we go through lots of examples in other videos. The median is the middle score and the mode is the most frequent. So those are all measures of location. Now, Knowing the location is interesting, but we could have lots of other differences. What about dispersion? We could have A, B, or C. We could have very tall and thin, very wide. What's the range? So some of the common tools to measure dispersion are the range of our data, which is simply the difference between the max and the min. The standard deviation, which is how far away the average mean in our data is. So we'll get into what one standard deviation, two standard deviations. Most of your data is within three standard deviate, plus or minus three standard deviations. A z-score is a way to standardize that. And coefficient of variance is a way to take the standard deviation divided by our mean. So those are measures of how dispersed our data is. So here's the standard deviation. How do we get this? So this looks very complicated, but if you think about it, let's walk through it because it's not that complicated. So what we're going to do is we're going to sum all our observation or all our sample points, and x1 or xi would represent each one of our sample points, and we take our sample point and divide it, and we subtract it from what our population mean is. So we're taking each one and seeing how far away from the mean the score is. Now, if you think about it, if we just did that with all of our numbers, we would sometimes be over, sometimes be under, and when we added them all up, we'd come to zero because that's what the average is, right? All the pluses would negate all the minuses. So we're going to square out to make all of these numbers positive. Because remember, anytime you square a number, negatives become positive. So we're going to take every single observation, compare it to the mean, square it, and add all that up. And then we're going to divide by n. And that'll give us what's called the standard deviation. Now, the standard deviation for a sample, that was the standard deviation for a population. Standard deviation for a sample would be the exact same equation. It would be all our x's minus our x bar, which is our sample mean, squared. But now because we've added in what's called a degree of freedom, because we don't know, we're somewhat guessing at what our population mean is and substituting in a sample mean. Down below we do n minus 1, and then we just take the square root of all of this to basically undo what we squared. And the same thing back here. We did the square root of all of this to essentially undo where we squared this stuff, and that gives us the population standard deviation, and this gives us the sample standard deviation. All right, now let's talk about some measures of shape, how it could look differently. So we could be skewed one way or the other. Here's some data where it's positively skewed or skewed to the left. Negatively skewed is skewed to the right. We could also have some measures of kurtosis. Is it very, very tall? All of these have basically the same range. They all have the same mean, but they're very different shapes. Tall and thin at the top, very flat at the top. That's called kurtosis. So our two things are kurtosis and coefficient of skewness, which you can get in Excel with Kurt and with skew. So skewness tells us if it's skewed to the right or the left. Kurtosis tells us how tall or how flat our data is. So those are measures of shape. So far we've had measures of locations, measures of dispersions, and measures of shape. Now, that's the three key ways to sort of describe our data. Now, sometimes we have what's called group data, and in this case, we'll take raw data and we'll take each one, x1 times the frequency of that observance, plus x2 times the frequency of that observance, add them all up to get our x bar. Now, proportional data, that's where we have categorical data or proportions, is the percent of the time we're successful. So if we're shooting foul shots, if we're pass fail, if it's accept, reject, order, yes, no. If you think about it, how are we going to add all those scores up? Well, the way we do that is we say, well, if I'm an 80% foul shooter, my proportion of success is 0.8. And then this sounds complicated, but and then our proportion of not successful is 1 minus 0.8. So if I'm an 80% foul shooter, 80% of the time I'm successful, 20% of the time I'm unsuccessful. If we had data on the number of on-time deliveries, we could count the number on time, divide by the total arrival, and we would know what proportion were on time. 12 defects out of 1,000, that would be 1.2% of the time we fail, and 98.8% of the time we're successful. So we'll use these proportions to calculate our statistics with categorical data. Let's talk about measures of association, how two sets of data may correlate to each other. Is there any correlation that exists between these two sets of data? Well, there's two tools we'll use. One is the covariance, which we won't use quite as often as the second one, which is the correlation, which tells us if there's a relationship between two variables. Are they correlated? So this is used very often to associate, is texting when you're driving a car associated with more accidents? And it helps us look at the data and say, yes, there is a correlation between those two. Now, we can get into that. That doesn't necessarily mean there's a cause and effect in everyone, because you've probably heard, if you've taken statistics or any of these stuff before, that you can come up with some crazy examples where, I can't think of them off the top of my head, but there's lots of examples where things could be correlated, but it may not be a cause and effect. Now, luckily, we don't have to memorize all of these different Excel things, because Excel has a great tool in the data analysis pack that you add on. So remember, you go to options and you add in the tool pack. If you go to data and you go to data analysis, and you'll get this laundry list of additional tools. There's one called Descriptive Statistics, which if you press that, you'll get all of these descriptive statistics. You'll get all the measures of location. You'll get all the measures of dispersion. You'll get all the measures of shape. And you get them all in one stop shopping. You go and you hit descriptive statistics, and you've got them all. And that's what oftentimes people will do when they first get a set of data, so that they understand what they've got. All right, let's touch on outliners. Sometimes we have data that looks like this, where we have one score that's way away from the rest of the data. Now, do we throw it out? Oftentimes people don't like to throw out data because maybe the data is, an event happened that day, like, airline flights on 9/11, or there's some interesting stuff I'll show you on breakups on Christmas Day don't happen. And there's a legitimate reason for that outliner. So what you do with outliners, and outliners generally most people would determine is a data point that's more than 3 standard deviations away from your sample or your population. There is no formal definition of what to do with this. It's a little bit subjective, but it's worth investigating. You need to investigate. Okay, did somebody just make a typo into the data and it's a typo, or is it a legitimate data point? So, if I've got somebody that's in my data that's 525 years old, I think it's safe to assume that there's a typo or there's an error, and I can throw it out. On the other hand, if I've got something that shopping volume on a certain day was especially high or especially low, I don't think we just want to automatically throw that out without a little research to understand if something unique was going on that day. Was there a record snowstorm? Was there tax-free day or something that made it unusually high or low. So with outliners, there is no, this is when you throw it out, this is when you keep it. It's very subjective to the person doing the analysis. The only thing I would caution you on is I would err on the side of including your outliners rather than just immediately dismiss them, because oftentimes there's some very interesting things and learnings you can come if the outliner, by researching the outliner. Okay. Now let's talk a little bit about statistical thinking. What are we going to do with all of this? So we've got all this laundry list of statistics. What do they tell us? So let's go through that a little bit, because that I think will help you. So let's one of the first things you'll do is highlight all your data and go to data analysis and say, hey, tell me all of the descriptive statistics. So this is what you'll get. Depending on I happen to have two columns. If you had one column, you'd only get one column. But let's understand a little of these. Okay, here's the mean. So the average of our data is 261.43. The standard error is 5.7. The median's 264 and the mode is 265. The standard deviation is 36. So we said the standard deviation, most of our data is plus or minus 3 standard deviations. So 36 times 3, round numbers, is about 100. 100 either side of our mean of 265. So we can conclude most of our data is between 160 and 360. There's our sample variance, our kurtosis, our skewness, our range, 170. Well, we guessed pretty good. Our min is 176. I think we just said between 170 and 370. Well, we're actually between 176 and 346. There's the sum, there's the count. So there's 40, the largest and the smallest, in the confidence level. So all of these will be explained, and we'll go through Excel examples in each one of the videos where we do the examples. But this is what you get when you do this descriptive statistics. So you get all of them there on one page. All right. Let's talk a little bit about what statistical thinking is. It's a philosophy of learning and action based on the following fundamental principles. So this becomes very important in business. All work occurs in a system of interconnected processes. In other words, there's a process chain, there's a supply chain. I do this, then this, then this, then this. Now, in most businesses, variation gives lots of rise to uncertainty. You don't want, ideally, a lot of variation. So understanding where you have variation and reducing it is one of the keys to success. So if you think about McDonald's couldn't be successful if the hamburger at one plant tasted different than the hamburger at the next store. One of the keys to McDonald's success, and a lot of fast food success, is I know when I walk in the door, I know what I'm going to get. I know I'm going to get the same McDonald's hamburger in New York that I'm going to get in North Carolina. And that's because they've gone through a lot of research to make sure that their processes deliver very little variation from hamburger to hamburger. So in order to do that, they had to get there somehow. They had to go through some process thinking and understand and manage the uncertainty. They had to make sure that the ketchup was all the same, that the policies were written, that, and you may know more about McDonald's than I do, but that the hamburger is there's a timer on it. There's a timer on the French fries. The oil is all the same in every store. So there's consistency so that they manage out the uncertainty. Now, they use the data wherever possible to guide them and make sure that they improve that decision-making process. Every time there's a deviation, it's investigated to improve the process. So let me give you a couple examples. If any are stock or bond thinkers, if you think of modern portfolio management theory. Now what this graph here is, this is your rate of return and this is your degree of risk on a stock portfolio. So here's how much money it returned. Here's the degree of risk or degree of variation. risk is in this terms very, very similar to the amount of variation. And what you can see, if they've learned, is in certain portfolios, if you mix it between stocks and bonds, there's an ideal mix where you can maximize your return while limiting your risk. Notice this portfolio returns much higher than this portfolio, but they have the same average rate of return over the number of years. So this average rate of return is nothing more than the mean. The average rate of return over, 35 years. So this average rate of return is the mean. And this risk is nothing more than the standard deviation in statistical terms. But modern portfolio theory has done this to manage out, hey, where would we be best? Are we best if we have 40% stocks and 30% bonds? Where is it best? Where do we fall along this curve given my risk tolerance? So this is used very often by portfolio managers, and it's all underlined by statistics. Very simple statistics. My average rate of return and my risk is measured by my deviations. It's also used very often in process control. So if I'm controlling the production line or I'm controlling the McDonald's stores, what I'll have is upper control limits, lower control limits, and I'll manage my deviations each day. And small deviations we wouldn't be terribly concerned about. But anything above or below our red lines, statistical thinking, outliers, these are how I control my processes in many or most businesses. And I become very concerned in research if it goes above or below the red line. So let's recap Chapter 4. We've explained the difference between a population and a mean, walked through some of the statistical notation, walked through measures of location, measures of dispersion, measures of shape, measures of association. We've introduced the Excel descriptive statistics tool. We've calculated or talked about proportions. You'll actually calculate all of these in the example videos. And we'll use the correlation tool. And we talked about the principle of statistical thinking. Any questions? Let me know. Thanks.